kind of details you might need to consider for string to int and int to string. Namely, let's start, which one was the first one? I don't remember what order I put them in. Huh? String to int is first, okay. Okay, so you start with something like that, okay? And so what's the first sort of issue that you have to deal with? Yeah, the string first has to be checked to be valid before you can do anything, okay? And so step one is input validation. Okay. Step two is once you know you have a valid input, then what? Well, okay, there's some minor details because that initial character could be a minus or a plus. And if it's a plus, do you really actually have to do anything? Because a number is assumed to be positive unless you specify otherwise, right? Okay. Um, so you just have to record somewhere if it's negative. Okay, then what? Yeah, so convert. Okay, so you've got to convert each character to a number, okay, but also do it in sort of a systematic way, or okay, so let's see, which way do I want to think about this? So you got to get all the digits and convert them into a number, right? Okay. Now, if we just take something like 1, 2, 3, 4, just for sake of example, okay, um, then there's sort of a couple things that we've got to deal with because, well, first off, how do I know if I've got a string, right, with 1, 2, 3, 4 in it? Well, then how do I know what, say, the um, well, okay. So let's say we're doing 1, 2, 3, 4, right? Which end do we start with? Well, okay. If we do that though, what's the problem? Okay, so the 1 is in which position here? Yeah, most significant, or in this case, the thousands place, right? Do we necessarily know that the first digit that we encounter is in the thousands place? Not necessarily, okay? Because what about if the number were a little longer? Right? Then who knows, right? Okay, so which end maybe should we start at? Well, okay, so what's the utility of starting at the other end? Huh? Well, okay, is there always going to be a digit in the ones place? Yeah, there always is a digit in the ones place. Now, that digit could be a 0, right? Okay, but there's always something there. And then how far do we have to move from the far right digit until we hit the far left digit in general? Like, what would it be useful to know about the string before we got into this? The length of it, okay, asterisk. And I say asterisk because what about if there's an initial plus or an initial minus? Okay, but knowing the length, wouldn't that be a useful thing? Okay, so let's say that. Uh, okay, and of course we've already done that, right? The string length counter. All right, and there's no point in computing the length until after you've made sure that the input's valid, right? So that's why I put that there. Okay. So how do we do this? Okay, so if we start at the far end of the string and we work backwards, then this hopefully will be easy. Okay. Um, Now, if we already know the length, that means that we have the value of a counter. Does the counter have to work, like when we use a counter, does it have to increment by one all the time? Or could we have a counter decrement by one also? Yeah. So in this case, you probably want to decrement by one each time rather than incrementing, since we're kind of counting backwards from the end of the string. Okay. So load in a character. Well, let me say a digits character. Um, all right, so if you load in a digit, how can you convert it to its numeric value? Okay, when I say load in a digit, you're loading it in as a character in ASCII, right? So what do you have to do? Well, it's kind of a similar trick to uppercaseifying or lowercaseifying, right? What was the trick for those? Huh? Yeah, you just had to subtract or add, depending on which direction you were going, some sort of number. Uh, in the upper and lowercase example, it was 32 or 20 hex in order to convert from upper to lowercase. So in this case, what's the ASCII code for, say, the digit 9? I don't know off the top of my head, but somebody pull up an ASCII table real quick and look. 39 in hex? Okay, so if 39 is the 9 in hex, how do I turn that into the number 9? I subtract hex 30, right? Which would be 48 as a decimal, obviously. Well, what's the ASCII code for the 8? 38. What do I have to subtract to get an 8 out of that? Same thing, right? So it's essentially the same trick as the upper or lowercase, right? It's just subtract from the ASCII value. Right? All we got to do is how do you make it go back to the, what is it? What is it in Word to go back? Shift tab. There we go. Okay. Um, yeah, well, we can subtract the fixed value from the character's ASCII value, right? And it either be 30 hex or 48 decimal, depending on which way you write it. Okay, so once you've subtracted it, you now have the numeric value of that digit. But then what do you have to do? You got to multiply by the appropriate power of 10, right? Okay, so like let's say that we start with the 4 here. Which position is the 4 in? It's in the ones place. So do I need to multiply that by a power of 10? well, 10 to the 0, which is 1. Okay, so maybe I'll make sort of an auxiliary counter that will count up by powers of 10, and I'll start it at 1. And each time I go through my loop, I'll multiply this other counter by 10, so it'll go 1, 10, 100, and so on, right? And then, all right, so then I need to add this to like an accumulator, or add this to a variable that starts with 0. Add it to a running total, right, of some sort. Okay, and then obviously at the end, if there was an initial minus sign, then we need to just make sure to throw that in. And then how could you make sure that you get a number negative? Like if you've got the positive version and you want to negate it, what could you do? Huh? Yeah, you could move in that number, or you could just subtract it from the 0 register. That's probably the fastest. Okay. And that way you'd have the negative version of it. Okay. Okay, so when I say by the appropriate power of 10, well, the 3, which is in the second position from the right, we would need to multiply that one by 10 and then add that to the total. And then we would have to multiply the 2 by 100, the 1 by 1,000, and so on. Okay, and so this secondary counter would be something that starts at 1 and counts up 1, 10, 100, 1,000, and each time we'd multiply by 10 as we move sort of right to left through the string. Okay, does that kind of make sense? Yeah? Okay, and then fix it if it's minus. Now, if you notice here, there's a lot of steps, right? And in particular, I think one thing that I've been, trying to get you guys to think of is, should we write a giant program that does all of this stuff at once? No. What would be much smarter? Like if I had given you this exact assignment in C, okay, what would you have probably done? Well, okay, the string length, obviously you wouldn't need to do anything there because there's already built-in function for it, but yeah. Well, yeah, you got to figure that out first, but make functions that handle each of these little pieces, okay, and then put the functions together, okay. Well, of course, if we do that, then what's the convention about functions? And this is where you guys you got to be careful. Excuse me. What do you have to do with functions? Huh? Well, yeah, but when you call, how do you call a function? Yeah, you've got a branch and link to the function, but you've also possibly got to pass it parameters and maybe get returned values from it, right? Where do those values have to go? The things that you pass to a function and the things that come from a function. They've got to go in x0 through x7, okay? And return values have to go in x0 through x7, but they've always got to go in order, right? So does this irritatingly mean that x0 has to get used for like a crap ton of different purposes? Yes, get over it. Okay, so the second thing is, do you have to put everything in one .asm file to do this? Of course not, right? Would you have to put everything in one .c file? No. You can have as many ASM files as you want, okay? You just have to obviously do a little bit more work on the compiling stage. Okay, so for sake of example with that, let's take a program that we've already written. think this is the one I want. Yeah, here we go. All right, let me open it in Genie. Okay, so this was a string that we, or excuse me, a program that we wrote that does what? It just computed the length and then printed it. Okay, and like in C, I made a function, right? So this is genuine function down here. So let's say I moved that to a different assembly file. Make sense? All right, so let me save a copy of this, and let me make a new new folder. Okay, strings2.asm, and then I'm going to cut this and make a new file. What did I call my function? Length. Okay, so I'll just call it length. Okay, now if I make this its own function, and obviously paste everything in, what's the one thing though that I've got to have? I've also got to have all this stuff. Okay, now I don't need these strings again because they're not useful here. And the name of my function is, of course, no longer main, but rather length. Okay, but otherwise everything's exactly the same. Yeah, and then over here on this guy, when it branches to length, if I were to just assemble this file and only this file, the assembler would say, okay, fine, but I just don't know what length is. So when you go to length the program, which is the second step when you use GCC or LD, then it's going to say, all right, well, you better have told me where the heck I'm going to find this length thing, whatever it is. Okay, in the same way that when we write a program and we use printf, have I defined what printf is anywhere here? No, of course not, right? But when I link it, because printf is part of the C standard library, the GCC or the linker, right, knows, oh, printf, yeah, I know who that is. He's over here. I'll link to that thing in the library. Okay, we're essentially doing the same thing, yeah. So is there a library like you see open up and pull up the file somewhere how you would actually linking the length file? Yeah, so is there like a source code, if you will, out there somewhere? Um, well, I guess yes and no. We're probably, well, we're going to be linking to a compiled version, right? So it's actual executable code. It's not going to be human readable. We could find it and disassemble it, okay, which is the process of taking a machine code and reverse engineering it to get back to the assembly, except it's basically almost not human readable at all, right? Because there's no comments, there's no labels, there's no nothing. You have to kind of reinvent the wheel there. Or in the case of something like C, where the library should be open, we could go find that source somewhere. Yeah. Okay, so got that. And so let's save both versions. And now I just need to go into my terminal and let's see. So we need to go to Documents, Examples, Multi-ASM. Okay, so I've got two assembly files in this case, right? And so I need to assemble length.asm and strings2.asm, but output to, let's just call this main.o. Oops. Oh, strings2, sorry. Okay, so that has made an object file that contains sort of both of their code together. Okay, and then of course I need to link it. So I'd say GCC main.o, and I just picked it that whatever. But then it still runs exactly like before. Okay. So isn't this kind of nice? Because you could take things like the length function and sort of spawn them off into their own little subroutine. Okay. Now, in this case, actually, does C have a string length function? Yeah. What was it called? Huh? One. Oh, no, it was what? strlen? Yeah. Okay. So, in the same way that I was using printf, could I have gone back in and changed, say here, to instead of using length, use strlen? Should that work? Why not, Ajay? You're shaking your head like it won't work. Well, let's find out, right? Let me just save this as a different version. And let me change this one to strlen, okay? And now I need to do, so this time I'm only using a single source file. Still works. Isn't that kind of nice? Yeah? Okay, so what functions from the C standard library are you guys permitted to use? All of them? Oh, but if I gave you all of them, then what could you do for string to int and int to string? You could just do it in one line. That'd be no fun. Yeah. Sorry, a little fun? Yeah. Nope. So you only get printf and scanf. Sorry. Okay. But point being, though, if you ever had to do something in the real world, yeah. Now, in this case, does it really matter with string length? No, because we've already written the function to do it. Okay. But, and this is the key, right? Why have I been such a hard ass about saying that inputs have to go in X0 through X7 and returns come in X0 through X7? Well, yeah, because if I want to use something from the C standard library, it's going to obey that same convention. And so I better know that convention in advance, right? Because where did string length, the built-in function, where was it expecting a string to be located? It was expecting the pointer to be an X0, and where was it going to return the length? Also an X0, okay? And if I don't know that that's the convention, then this isn't going to work. You have a dubious look on your face, Drake. Why do you have a dubious look on your face? No. Are you dubious about the calling convention? No. Okay, are we clear about the calling convention? Right? Thou shalt respect it. Okay, or as I told Caleb the other day, right? You will respect my authority. Right? Complete with the Cartman meme. Okay. All right, so, yeah. You can, of course, mix C and assembly in lots of other ways, and I'll show you some of those later. But, okay, so if we go back to sort of our high-level kind of approach here, right, how much of this stuff could be turned into separate functions, right? A lot of it, right? Depending on how you want to organize things, well, feel free to do so, right? Okay, for example, the input validation could be a self-contained thing, right? And you know, how are you going to input validate something? Right, so how do you look at a string, one of our strings for this, for the purposes of this project or this program, and decide if it's valid or not? Okay, so what's valid? What's a valid character for the very first character of the string? A plus or minus, or a digit, right? 0 through 9. Okay, now, would we write 0, 1, 2, 3 as a number? Probably no, but is there any harm in keeping that as a possibility? No. Okay, so the first character could be a plus, a minus, or the characters for 0 through 9. What about all subsequent characters? They have to be characters 0 through 9. And if any of them aren't, what do we know that we've hit? No, until we hit the null terminator, right? We know that we have an invalid string, right? And if we get to the null terminator and we haven't hit an invalid character, we know that we have a valid string. Okay, well, great. Now we have a basis for a decision. Okay, good. So, so don't try and do all of this stuff at once, right? Build it up, right? We already have the string length function, right? Because we wrote it in class. And the input validation, right? Write that by itself and test it. And then get the other stuff in, right? Don't do all this at once or else it's gonna be a train wreck. Okay, now, the one other thing about this. What's the, did I say we were gonna do this with a 32-bit, or what size number did I say we'd use? 32 or 64? Thought I said 32-bit. Yes, okay. So 18 bytes, all right, which means how much data on the stack do you need to allocate in order to store the string? If it's an 18 character string, okay, you only need 19, right, because of the null terminator. All right, but how much data do you actually have to allocate on the stack to do 18 characters? No, it'd be 32 bits, or bytes, excuse me. Okay, why 32 and not 19 or 18 or whatever? Yeah, the stack pointer has to be a multiple of 16, okay? So you have to round up to the nearest multiple of 16 in terms of allocating that space, okay? Now, does that mean that we're wasting a little bit? Yeah, and that's okay, right? Now, why did I pick 18 bytes? Okay, I didn't just pick that out of thin air, right? So if we, well, here, let me just pull it up on Canvas. The details of the, all right, which one is that? D? Yeah, okay. So 64 bits, right? The largest number that you can store as a 64-bit integer is 2 to the 63rd minus 1, okay, as a signed number, right? That has 19 digits. So if we limit ourselves to 18 digits, then we won't have to worry about some weird overflow problems or anything like that. Okay, so that's why I just picked 18 digits. mostly arbitrarily, but yeah, because if you have a number that say, like, let's say you had 32 digits, you can't store that in a 64-bit integer anyway, right? And so we'd have to go back and rewrite stuff and define 128-bit integers like we did on one of those assignments. Okay, we could do that, but that significantly complicates the arithmetic. Okay, yeah. Ah, good question. No. Okay. So, well, I guess yes and no. The Well, okay, so that's a good question. Let's demonstrate this. Okay, and how I'm going to demonstrate this is let's go back to here and let me assemble and compile with the debugging. Okay, so this is the one where we had the length function spawned out as a separate subroutine. Okay, is that okay? Okay, so I put a breakpoint at the first line, which was main, right? And let me step. Okay, this is our stack pointer. Okay, right after the program started, because what was the first line of that program? Well, I saved over it, but what did I call it? Strings 2. All right, what was the first line? Yeah, so put X20 and X30 or X29, X30 on the stack. Okay, great, right? And so we've already done those two. And then now we're about to branch to link. So that's the next instruction that's about to get executed. So our stack pointer started blah, 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 070. Okay. And if I look at memory, what's sitting there on the stack? Okay. So the stack is, let's be clear, okay, only the top row here. Okay. And what's maybe a little bit annoying about GDB, like, okay, so this is a direction thing. Which way does the stack grow? Up or down? Well, what does down mean, Cole? Yeah, from high memory addresses to lower memory addresses is what we mean when we say down. Okay, does that mean that it has to be down visually? Okay, because which direction are the memory addresses organized here when GDB prints them? What's at the top? A lower memory address, not a higher memory address. Is that mildly annoying? Get over it, right? You guys are big boys and girls. This is CS241, damn it. So get with the program, pun intended. Okay, but what is sitting there on our stack, which is, to be clear, only the very top row of this thing, what's there? Excuse me. What's on the top row of the stack? What's the first two entries? What are those? Huh? It's not a pointer. Well, it is a pointer, but which pointer? Sorry. The blah blah blah. This guy here. This. Okay. That was the original value of our stack pointer, which happens to be the same as the original value of the frame pointer. Okay, so X29 is actually the frame pointer, not the stack pointer, but the two start as the same thing. And I don't want to talk about what the difference is right now. Okay, and then what's in the other two entries here? This 4008F4, and then of course it's padded to the left by a whole bunch of zeros. What was that? Where did that come from? What came from X30, right? What was X30? Okay, so X29, X30 are real special, right? What is X30? The link register. Okay, what is the purpose of the link register? Okay, when we branch to a subroutine, how do we know where to go back to? The link register is what tells us this. Okay, so when you BL to something, okay, let me write this on the board. If you BL to, I don't know, func, whatever function is, okay, that instruction does what? It's going to set the program counter to the starting address of func, okay, wherever that piece of code starts, okay? And then when the program keeps running, the program counter is going to load in the instruction stored at that memory address, increment, decode it, do whatever it says, etc. Okay? But it also is going to take well, okay, let me actually say this in the opposite order. Okay, it's going to first put the current PC value plus 4 into X30. Okay, why plus 4? Okay, the current PC value is the instruction I'm on right now. Okay, but why plus 4? Because what's the instruction right after that? How many bits does it take to encode every instruction in this architecture? Every single instruction, how many bits? I'll take 32 bits for 500, Alex. No? Okay, surely to God, I've said this a million times before. Well, it shouldn't be a guess, Cole. It should be a, yeah, we just know this shit. Okay, so why don't we just know this shit? Or why are we not remembering this shit right now? Because it's 8 in the morning? Hmm? Hmm. There are actually some 16-bit instructions, but those are part of the thumb subset, right? Because if you've got ARM, you could have thumb. Okay. Hey, I didn't make that up, okay? They did, right? And there's another book that defines something that's sort of ARM-like, and he calls it leg, because, yeah, that's real funny, right? Okay, now, also, I guess to be clear, did ARM actually start as meaning like an appendage of the human body? No, it meant Acorn Research Machines, okay? Yeah, and it's sort of, it's actually an English company, British company, well, until NVIDIA bought it, or tried to buy it, I guess. They're still mired in antitrust hearings and such. Anyway, the reason that ARM got started was actually because, so the BBC Micro, you guys have heard me, wax poetic about my favorite old computers from the 80s, right? Including the venerable Commodore and so on. Well, there was another one, the BBC Micro, okay, which was sold and designed basically for the British school system, and to be super cheap so that British students could afford one. And it had a 6502 in it. Well, as they were developing sort of new models and hitting the limits of what you could do with the 6502, they got kind of irritated and said, fine, we'll just make our own damn chip. And that's what started the ARM lineage. Okay. Anyway, all right. So it's going to take the current value of the program counter plus 4 bytes and put that value in X30. And then it's going to set the PC to address of func. Okay. Got it? Now, inside func, what is going to be down there at the very, very bottom of it? What's the absolute last instruction that a subroutine executes? The return. Okay, and that's sort of the symmetric piece that's going to go with the BL. Okay, so when you hit the return, what happens? Okay, well, actually, I guess it's just one thing, right? The PC is changed to what's in X30. Okay, and so if we had some function that was like if we had a function that was like do some stuff, and then there's a BL to func, and then there's some more stuff, okay, then when we hit line 2 here, BL func, what happens? Current value of the program counter plus 4 bytes goes to X30. Program counter gets set to the address of func. So now we're down there and doing func wherever it is. Okay, so let's say it's down here, func, and it does stuff, and it rets. Okay, so it has a ret at the end. Okay, so we jump down here, we do some stuff, whatever it is, and then eventually we hit a ret. And what does the ret do? Returns by, yeah, X30 goes into program counter, and X30 was the old value of the program counter plus 4, which lands us right back here, one line after the BL func. Okay, now, how many link registers do you have? How many X30s are there? It's almost a stupid question when I word it this way. There's precisely one of them. So what happens if you branch to a subroutine that needs to then branch to another subroutine? You've got to preserve the old value of the link register onto the stack, which is why what's the first and second to last instruction of every program we've written? Store pair x29, x30, stack pointer minus 16, right? Okay, basically preserve the old value of the link register in case we need to update it with a new one, and then at the end, pop it off before we ret. Yeah? And this, of course, is what makes recursion actually work. Okay, all right, so if we go through the rest of this demo, right, then what should we see? Okay, well, we should see exactly this. So what am I about to do? Huh? What's the next instruction that's about to get executed? Okay, I'm about to hit the length instruction. Okay, now I haven't executed it yet. That's the next one. So what's our program counter's value at this exact moment? 614. Okay, and if I step, I'm now in the length function. Okay, and what's my program counter now? Okay, something different, right? But what is my stack pointer? Same thing, okay? And so if I step, okay, what's on the stack here? Okay, what is this that was on the stack? And let me scroll so you guys can see it well. Okay, what was that thing? That was the frame pointer and the original value in X30. What's above it? The new values that we just pushed. Now, in this case, the frame pointer doesn't change throughout your program. Okay, so did we ever really actually have to store X29 ever? No. Okay, you're just doing it because I told you to. Yeah. Okay, but point being, it's the same stack because this is the same program. It's not a different program. Okay, that's good, right? Because it means if you've got data on the stack, you can get to it anywhere. Okay. The other thing though is, well, if you have subroutines like this and you want to like pass a string, right, to this length function, what did I really pass to this length function? I didn't pass the string. I can't pass the string. I passed a pointer to the string, okay, which is just a 64-bit number. That's why I put it in X0. Yes. Yeah, okay. The program counter is a pointer to where the next instruction is going to be loaded in from memory. Okay, so actually in some architectures, it's called the IP or instruction pointer rather than the program counter. Yeah, honestly, instruction pointer I think is a better name. IP for short. I'm sorry? Uh, the program counter? No, it's a register. Now, you could, of course, store its value to the stack if you wanted to, okay, but it is its own register, and it's separate from X0 through X31, okay? It's sort of a specialized one. Every single architecture has to have one of those things. You know, so some architectures, like, so the 64-bit ARM, we have 32 registers basically. Now, some of them have specialized uses, yes, but we basically have 32 of them, right? 32-bit ARM had 16 registers. Again, some of them with specialized uses. But program counter and stack pointer are sort of dedicated registers that are separate from that general purpose pile. Now, like I said, some architectures have very few registers, right? So if you go way back, 6502 kind of, early, days, there were very, very few registers, but the program counter was always one of them. It has to be there. In fact, speaking of old architectures, I thought I would mention this. I put it in the Discord channel. What was yesterday? Yesterday was the 15th of November in the year 2021. What happened 50 years ago yesterday? The Intel 4004 was released. It ought to be, right? So the first commercial microprocessor, the Intel 4004, 50 years ago yesterday. It's kind of freaky when you think about it. It wasn't that long ago, but yet it was 50 years ago. Okay. Yes.
Just a really interesting question. Was that the processor that was used in the Apple
No.
I?
Apple I also had a 6502 in it.
Okay.
Yeah. And the reason for that was because the 6502s were dirt cheap in comparison to other processors of the day. Yeah, so the Apple One and the Apple II both had the same processor in them. But I mean, basically, right? Um, the yeah. So the Intel 4004 was designed for a calculator, um, and it was the architects of it basically were like, why should we design a whole new microprocessor every time we need to, or chips and stuff, every time we need to build a new product for somebody? Why don't we just design a sort of general set of a couple different chips that are all part of a family that can be used for lots of different purposes, right? Like you could put a calculator or they build a cash register out of the exact same chips. Wouldn't that make a lot more sense? And thus was born the Intel 4004. And everything that descends from that is magic. Now, it is not, in fact, the very first microprocessor, but we didn't know this until the 90s. Did I mention this to you guys last week? I don't remember. Maybe it was to my 101 class. The very first microprocessor, and I don't even remember the name of it, was actually developed for the F-14 Tomcat. Okay, but it was classified, and its existence was classified until the 90s, so nobody knew about it. Okay, so they beat Intel by about 6 months, and it was basically for the flight computer on the Tomcat. Now, how many of you guys know anything about the F-14? Right? What made the F-14 really cool, other than Tom Cruise and Top Gun? That's the plane that they fly in Top Gun, by the way. Huh? What? It is. It. I wouldn't say it's the greatest movie ever, but it's definitely a good one, right? And of course, you all have Highway to the Danger Zone going through your heads right now. And if you don't, you fail. Okay, so one of the reasons that the F-14 was so unique was what could its wings do? They could tilt back and forth. Okay, for low speed flight, they'd be tilted forward and wider. For high speed flight, they'd tilt back. Well, you kind of need a computer to figure all those details out of when to move the thing, right? And that's why they developed this computer for it, so that it could actually do that. And thus gave us the movie Top Gun. So you're welcome, okay? Because we couldn't have had Top Gun without microprocessors, because we wouldn't have had an F-14 without them. Okay, good. All right, so great, right? Split things up into subroutines. That's fine. Uh, all right, now back to what's the other thing we've got to do? All right, into string. Okay, first off, if you have a number, the number will only, like when I type the minus sign here, is that really part of the number? As a string, yes, but as a binary encoding thing, no, right? Because how are numbers encoded in as integers if they're negative? Right, you got to go do the whole two's complement business. All right, so if it's negative, what would probably be a good idea to do first? Just make the positive version of it, and then you can always put a minus sign in front later. Okay. Um, okay, so let's concentrate on just say 1, 2, 3, 4. Okay. And I need to get, like before, we should start at the far right end. Okay, because that's the least significant end. And we don't necessarily know how many digits we have in advance, although we could we compute the length here, the string length? Would that work? No, why not? Because it's not a string, it's an integer, right? We don't have a string yet. The whole point here is to make one. Oh, well, that's awful. Okay, so I need to get the 4 out of here. how do I get the 4 from 1, 2, 3, 4? Huh? Not quite. Okay. If I divide by 10, I get 1, 2, 3, remainder 4. Okay. However, what does the division operator on this processor do? Does it give me the 4 or just the 1, 2, 3? It only gives me the 1, 2, 3. Okay. So how do I get the remainder? Well, we get it by taking the original number and subtracting 10 times the dividend, or sorry, the quotient, and then what's left, of course, is the remainder. Okay, and notice what we're doing here is an addition, or well, subtraction in this case, but it's a multiplication plus an addition, right? And if only there were an instruction for fuse, multiply, add. Wouldn't that be great? Yeah, okay. Okay, so that gets me the remainder. All right, and then what do I do for to get the 3? Well, I already have the 1, 2, 3 here, right? So what do? Just repeat this process. So 1, 2, 3 divided by 10 is 12. 1, 2, 3 minus 10 times 12 is 3, the digit, okay? And if I know the digit, the numerical value, can I convert that into an equivalent ASCII character? How do we do that? Yeah, just add that fixed offset that we were subtracting in the last version. Okay, and then we just continue. Okay, until what happens? How do we know when to stop this process? Okay, because we don't have a length necessarily anymore because we're not dealing with the string to start with. So how do I know when I should stop doing this division and subtraction business? Huh? I get 0 as the result of the division. Okay, that would happen equivalently if the number that I'm dividing into is less than 10. Okay, so either way you want to think about it, right? Because if I do something that's less than 10 divided by 10, what am I going to get? 0 with, and then everything is the remainder. Okay, so either way you want to think about that, that's what that would work. Okay. Now, like I said, what about if the original number is negative? What would probably be a good idea? Record that it's negative, make it positive, do everything, and then throw a minus sign out front. Okay. Yes. 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 So you could subtract, so to take a negative number and make it positive, you could subtract it from the 0 register and that'll positivize it. Okay. Now, you could also multiply it by -1, right? But the subtraction or addition version is actually faster, right? It's more efficient for, in this case. Yeah, Kate. Yes and no. Um, because if we're going to start counting from the far end of the string, the minus sign still matters in terms of figuring out where that memory address is. Okay, but the counter's value, like yes, that is an issue because then you might go into the minus, right, in this computation. So Yeah, you're going to have to be careful with that and figure out how to deal with it. Yes, it will be a problem. Okay, so what's going to be annoying on the int to string is that in a sense, it actually makes sense to build the string backwards, right? Because what's the first character I would put that I've figured out here? The 4. Okay, so let me write down the 4 in a memory address. And then what's the character after that? A 3. And what's the character after that? A 2. And then the character after that is, say, a 1. And then let's pretend that the number that I started with was minus. So I know, I'm finished with the conversion because I've gotten to the point where the division, the quotients are 0. Equivalently, the number that I'm working with is less than 10. Okay. And so I know that I need to put a minus sign in front, say, and so let me just throw a minus sign on there. But this is in reverse order, right? Could I write another function to then reverse the order of the string and put the minus here, the 1 there, the 2 there, the 3 there, and the 4 there? Yeah. Okay. Now, that's not the only way to approach this, but that might make for an easy way, is build the string, realize, of course, it's going to be in backwards order, and then reverse it afterwards. Okay. Is that simpler than trying to reverse it as you go? Probably. Okay. In particular, do you know how many characters you're going to need in advance? No. Okay. So I think it's probably easier to build it in reverse and then reverse it. Okay. Personally, I don't know. Maybe there's another elegant way to solve it, and I look forward to seeing what you clever gentlemen can come up with. Right. Because sometimes you guys really surprise me and come up with ways I didn't even think about. And that makes me very happy. Right? Nothing is more entertaining when I look at something and I'm like, wait, what? Oh, that's slick. Right? Yeah. Okay. Drake, did you have a question? You had your hand. Yes, both are. Okay. What's the difference then in terms of the user input? Yeah, percent %I or LI or whatever, right? As opposed to percent %S. Okay. Now, the other thing with when you're doing the percent %S for the string version, what are you going to put in front? Well, or in this case, 18 or what? Yeah, 18, I think I said. Um, but yeah, you're limiting the number of characters. Now, in the int version, do you need to limit the number of digits? Actually, I would. I would limit it to 18 digits, uh, simply because, well, okay, if the number's too big, then this isn't going to work, right? Because it's going to overflow and get weird. Okay, so basically, just make sure it's within the bounds of what you can store in a 64-bit int, right? And yeah, okay. All right, this isn't rocket science, but it is quite a bit, because it's putting a lot of stuff together. Okay. Um, yeah. I did want to talk. Well, any questions about that? I did want to talk about one other thing kind of quick before we finish. No? Okay. Which is the test instructions, because there's actually sort of 3 of them, depending on how you want to count. And I wanted to make sure that you guys were clear about the syntax for um, each of them. Okay, I think I put it in here. And if not, I'll just download it again. Nope. All right. I thought I had put this on Canvas, but clearly not. Okay, so this is a little cheat sheet that guy at the University of Washington produced. And it's sort of a quick reference card for the entire instruction set. And in particular, I mean, there's a lot of this stuff that you can ignore, but in particular, it's handy because we've got the quick instruction set, all the arithmetic instructions, all the logical and move instructions, all the load and store instructions, and so on, okay? But there's three instructions that I want to pay attention to right now, okay? The test instruction, TST, what that does is it logically ands against the thing that you give it, okay? So if you want to know whether or not something matches a bit pattern that you've selected in advance, okay, then you can use the test instruction, okay? If you want to test a specific bit of a number, just one bit, and determine if it's 0 or 1, then you're basically using TBZ and TBNZ, okay? And what you give there is you give which register you're looking at, of course, that makes sense, and then you give the bit number that you want it to check, okay? So the bit number, what are the valid bit numbers to check? Well, how many bits are in any of these registers at most? Yeah, okay. So the bit number that you examine is 0 through 63. Okay, so the far right bit is the 0th bit, not the first bit. That's just the order of counting. Okay, so if you want to check if a number is odd or even, for example, what would you do? If you want to check if a number is odd or even with the TBZ or TBNZ, what would you do? Which bit? Which is the 0th bit. Okay, because that's the ones position as an integer, and hence, if that's a 0, you know you have an even number, and if it's a 1, you know you have an odd number. Okay, what about if you wanted to check if your number was positive or negative? The first bit, which is really bit number 63, right, because they go 0 to 63, right, is the convention, right? Okay, so, right. So if you want to test against a specific pattern, use the TST followed by a branch, okay? If you want to test a specific bit, then use TBZ or TBNZ, and those are basically a test and branch built in together in the same way that we also have, wherever it is here, oh yeah, right above it, right, that we use CBZ and CBNZ, right? Compare branch on 0 or non-zero, depending on which way you want to do it. Yeah.
So is TST like CMP?
Mm-hmm. Yeah, TST is basically like a CMP. Okay. Um, it uh, now truly, okay. I should let me make sure that I'm clear on this. Let's see, where is it? This. Truly, what TST is doing is it's really and S up there at the top. Okay, it's doing logical and. Okay, and what's the S mean? So if I do and S, what does and S mean? Do a logical and then the S says set the flags as appropriate. Okay, the 0 flag, the carry flag, et cetera, et cetera. Okay. Um, Yes. So the TST is really an alias for that. But when you're reading your code, it's easier to see TST than an and where you're like, well, why are you anding here? Okay. Okay. So does that kind of make sense? Yeah. Let's see. We talked about the shifts and the rotates and stuff before. Right. The shift and the rotate, those would be really handy for the int to string, except what's the problem? When we shift or rotate, what are we shifting or rotating by? What is that a tantamount to doing? That's division by 2. But what do we need to divide by when we're doing the int to string stuff? Womp womp. 2 and 10 are, last time I checked, not the same number. Okay, we could also divide by 2 and then divide by 5, but whatever. Okay. This, by the way, actually, I guess brings up an interesting problem. Would you guys agree that the fact that we have a division operation is what's going to make this program not so horrible? What would happen if there weren't a division program? I mean, a division function. Oh, that would suck, wouldn't it? So what happens, like, how would we approach this if we didn't have a hardware divider or multiplier? Yeah. Well, what is division, pray tell? Yes. Okay, but I can't think of fraction because I'm thinking of integers. So what does fraction mean? Nothing. Right, it's not relevant. Okay, only because we're dealing with, sorry, only because we're dealing with integers. Nope. Well, let's say you don't even have floating point hardware. Huh? No, we'll go back to the 80s. Right? Well, okay, Cole, at the rate this is going, guess what one of the assignments I'm going to give you next semester is going to be?
Multiply by fraction.
Do this without multiplication or division. Okay? Yeah.
I was going to say you can subtract.
Yeah, division is really repeated subtraction, right? So in the same way that multiplication is repeated addition. Now, there are clever ways of doing multiplication, right, on a computer. Like, has anybody ever seen the Russian peasant method for multiplication? Yeah? No? No? All right, look it up on Wikipedia. It's actually really clever. Okay, and if you look at it in base 10, you think, oh, this is the silliest thing ever. But then you think about doing it in base 2, and it's like, oh, that makes so much sense. Okay, right, you'd have to do some sort of repeated subtraction routine. Okay, anyway. All right, it's 9:15. We should quit. I will see you guys on Thursday.